I was actually told it was hard to hear me last time, so I'm going to try to increase the volume on this. I don't know how to do that though. All right. So while we're waiting, so we briefly introduced convolution last time, and I think you did a little bit of more practice in the discussion session, and you have a lab going on where you get to play around with the convolution operation. But it's important that you understand the mechanics of this, okay, for our subsequent discussion. So while you're waiting for another couple of minutes, why don't you work on, what is u star u of n, where u of n is the unit step. It's a good thing to play around with while you're waiting instead of just staring at the ground board. I should have made this a quiz, pop quiz. So how many of you have no idea how to do this? Okay. You can talk to people around you, either to commiserate or to get help. Yes. Yes. Yeah. That's what that expression at the top says to do. Yes. So that's one of the properties we'll discuss today. Short answer, it doesn't matter. You get the same answer. But we'll see why. According to the definition, the second term gets flipped and dragged. But it turns out that even if you apply it to the first, you'll get the same answer. That's the commutative property of convolution, which we'll talk about in a second. So this is a quiz, guys, that once you just walked in, it will count for 50% of your grade. So if you came late, too bad. Just kidding. It's a self-quiz. Just make sure you understand how convolution is done. In lecture, I can't spend too much time, repeating examples or examples of convolution, but you need to be comfortable with the mechanics of it. So I think it's time to start. So let me just do this, and I will never again work on another convolution example. But so what this tells us to do, if we just look at the first expression in the summation, is to take the first signal. In this case, most signals are the same, so it doesn't matter. And make it a function of k. So we replace n with a dummy variable k. I can do better than that, because there's a trick to do this. See? Okay, so we'll just draw u of k, right? It's going to look like this. So this is k, and before k equal to 0, it's all equal to 0, right? So that is u of k. Now, the second term you have is the second signal flipped, because k is now the variable we are looking at, right? It's flipped and dragged by n. So what happens if I take the unit step and if I flip it and drag? So it's going to, once I flip it, it's going to occupy the negative axis of k, right? And once I drag it, it will also start trespassing to the right axis. So it will end at what point? At n, right? So now it's going to look like this. So when flipped, it would look like this, right? That would be u of negative k, right? But I'm interested in not just flipping, but also dragging. So let's look at u of n minus k. So that will shift it to the right by n. So n will be the entry where this stops being 1 and goes back to 0, right? And then we have to multiply those. So multiplying is easy because they're either zeros or ones. So let me just copy this. Copy, paste. Can you see this or not? Can you see it? See the bottom? No? Now can you see it? Okay. So I'm trying to look at the product of u of k and u of n minus k. Clearly, u will erase anything that was on the negative end. So these guys will go away, right? So u of k times u of n minus k as a function of k will look like this. Everybody agree with that? Yes? Okay, so we now have what's highlighted here, right? So it's the product, it's a function of k. But then we also have to look at the sum. We have to sum over all k's, right? So then I need to sum this over k. And what does this give me? Yes? You have an answer or you have a question? Yeah, go ahead. Right. So the picture I have here is for n positive, right? If n is negative, it will of course be on the other side. If n is negative, there's no overlap of these things, right? So it's flat equal to 0, right? So that's going to give you 0 if n is negative, because the two signals don't overlap anymore. If n is 0 or more, how many non-zero entries do you have? You have the one at 0, you have the one at 1, and the one at n, right? Altogether, I have n plus 1, because even when n is equal to 0, I have 1, right? So it's equal to n plus 1 if n is 0 or more. Okay? So therefore, the answer to the problem, the convolution of the unit step with itself, is a new signal that looks like this. It's zeros before time equal to 0. At time equal to 0, it jumps to 1, and then it becomes 2 at time equal to 1, and then increases linearly from that point on. Right? That's the convolution. Okay? So convolution is an operation of signals. You take two signals, take their convolution, the result is another signal. All right? And the mechanics of this is as such, you just keep one signal fixed, flip the other one and drag it by n, multiply sum, and whatever comes out will of course depend on the value of n, and that defines the signal as a function of n. Now, those of you who had no idea how to start, do you have some idea now? Yes? Okay, so when you work on the lab, there are actually examples where you do this, and make sure to pay attention to them. Any questions before we start the main part of the lecture? No. Okay. All right, so we are going to talk about some properties of convolution. And one was already asked, does it matter which one I flip and drag and which one I don't? Well, the answer it doesn't, so there's the commutative property. But we'll talk about some others as well. So properties of convolution. So the first property is that if I take any signal x and take its convolution with the unit impulse, the answer is x itself. Okay? So convolution with the unit impulse changes nothing. You get the same signal back. All right? So in a sense, the unit impulse is the identity element when you're applying the convolution operation. All right? Why is this so? Again, let's recall the mechanics of the convolution here. So x is a signal, right? So to do the convolution operation, I make it a function of k being a dummy, so x is going to look like some kind of signal, right? So let's call this x of k, right? And the second signal is delta. And to that we will flip and drag, right? We'll apply those operations. So what happens if I flip a delta? Delta is a singleton at time 0. If I flip the time, it's still there at 0, right? So nothing changes if I flip. If I drag, it just moves to n, right? So delta of n minus k as a function of k is just a delta moved, now centered at n. Okay? So when I multiply, then what happens? Delta is almost always 0 except when the time k happens to be n, right? So their product will also give you all zeros, right? Except at k equal to n, which is here. And what's the value there? X of n, because delta itself has unit value, it's the unit impulse, right? 1 multiplied with x of n is the value of that particular signal at that time, right? You'll get x of n, right? And then I need to sum this over all k's, and you're summing a bunch of zeros. The only non-zero element is x of n, so what comes out is x of n. Here's your proof, okay? Purely graphically. All right, so delta is the identity element, the impulse. Unit impulse is the identity element when it comes to convolution. Questions? Clear? Okay. So, wait, I'm not waiting. Second property, very similar. When I take a signal and take its convolution with delta, but not the same delta, we're going to shift delta, okay? So convolution of x with a shifted delta is, and what do you think that would be? Again, the picture would be very similar to before. I will have the signal x of k as a function of k, whatever it looks like, right? X of k, right? And then the other signal is an impulse centered at capital N. I have to flip it and then drag it, right? What happens when I flip an impulse that's centered at capital N? It moves to negative capital N, right? And then I drag it by little n, so it moves to from negative n, it moves to little n minus n, right? So, all clear here? So this is delta of k minus, wait, delta of n. Yeah, I don't even need to write what it is actually. So this is delta after being flipped. I mean, this delta after being flipped and dragged, right? Everything else is equal to 0. So you multiply them. Again, it picks this value here. Everything else gets zeroed out, right? And that value here, of course, is x at time little n minus big N, right? So the answer is another impulse whose value is x of little n minus n. And then I sum this over k, and it gives me x of n minus n. Okay? So it's important to understand what's going on here. So when you take the convolution of a signal with an impulse, nothing changes, you get the same signal back. If the impulse is a shifted impulse, then you get to shift the signal itself. Okay? So those are two important properties. Any questions? No questions because all clear, or you don't even know what questions are? Okay. Yes. Intuition for the shift and the impulse. So which one are you asking? Why? So let's see. So are you asking why after taking this signal, which is a single impulse at capital N, I flip it and drag it, I get this? Is that the question? Okay, well, so this signal is, just by itself here, right? Everything else is 0, right? If I flip it, it's going to go to negative n. And if I drag it, it will move by n. So whatever is at negative capital N is now going to be n minus n. So that's how we got this. Does that make sense? Sort of? Okay. Not to put you on the spot, but did you play around with
Yes.
the lab? Oh, okay. All right. Still? Okay. Any other questions? Yes. Yeah, so when I write this, yeah, you're asking a good question. So yeah, in this representation, little n is the time variable, right? So when we're doing convolution, remember, we have to first write everything in terms of k. So we forget about n, right? So we use the dummy variable k. N just becomes a parameter, which tells me how much to shift the second signal after flipping it, right? And then I do these summations and all that, and it gives me a result that depends on what little n was, and that defines the resulting signal that's a function of time variable n. Does that make sense? Yes? All right. So, is there anyone here from the math? Math? Okay. So you probably start hating me already when I wrote the second expression. Did you? Or you didn't catch it? So, in terms of notation, star defines an operation between two signals, right? So when I can, okay, I should write this. When I'm taking the convolution of x and h, I try to write xh because that's a new signal, right? And because that means, x star h is a signal, right? X is a signal. In other words, it's a map from the integers to reals, right? And so is h. And then x star h is also a signal, right? So when I write x of n, on the other hand, what is x of n? Is it a signal? It's x of n is the value of the signal at when time is equal to little n. So this really is a different object than h and x, which are signals. This is just the real value, right? So this is the real. So that's why I prefer to write this. X star h is a signal, and when I put the n, it's the value of that signal at time n, right? But sometimes you'll see me doing this. And if you're a mathematically advanced person, you may not like this. Okay? Really, I mean the same thing as x star h at time n with this expression. Although, if you start, questioning this notation, really, there is no definition for the convolution of two real numbers, which this amounts to being, right? X of n is a real, h of n is a real, okay? So, whenever I can, I'll be precise and use this one. Sometimes I'll have to resort to this. By the way, the textbook does this left and right, okay? Sometimes it's just inevitable. Or if I choose not to do it write it this way, the notation will get very clunky, right? I had to use it here, for example. Why? If I want to be a little more precise in my notation, I would have to first define, say, a delta hat signal. According to this relation, delta hat of n would have to be defined as delta of n minus n, right? And then I would have to say, so this is the definition of delta hat, and I would then say x star delta hat at time equal to n is x of n minus n, right? Alright, so that would be a better way of writing this. But it gets clunky and, it becomes a turn off for those who don't care that much about mathematical accuracy or precise notation. So keep in mind that this will be used now and then as a shorthand for, the convolution of two signals. Okay? So when you see this, interpret it as this. Yes? Okay? The mathematician satisfied? Alright. I've been teaching this course several times. Not in the recent several years, but before that I taught it many times. And every time, I thought about, wouldn't it be great to teach this course in a very mathematically precise way with notation and everything super precise and all the convergence properties laid out that we'll see later for transforms. If you do that, the course becomes sort of like half function analysis and half signal processing, okay? And so, you have to take shortcuts. My strategy, after thinking about this for years, is to be honest when I'm committing mathematical sins. I'll just say, I shouldn't have done this, but I'm doing it anyway, okay? So that way you know that, something is a little offensive to a more mathematically advanced person. Alright, so everybody with me? Okay. And I also don't want to lose the non-mathy guys trying to please the mathy types, so it's hard to find a way in the middle. Alright, so 3, the third property. Third property is a question that was asked already. It's the commutative property. It does not matter which of the two signals I flip and drag when I'm doing the convolution operation. So x star h is the same as h star x. We just defined a convolution of x and h to be this, where we keep x alone, we leave x alone, and then flip and drag h, right? And then sum. So let's take this as the definition, and let's show that there is no discrepancy if I do the flip and drag to x and keep h, leave h alone. It's easy to do that. All I have to do is a little change of variables. Okay? If I define this to be a new index r instead of the index k, right? So I'm just I'm just changing how I'm doing the counting. Instead of counting over k, I'm going to count over n minus k, right? Which I define to be r. So with this definition of r, what happens to k? What is k equal to? k is then equal to n minus r, right? So then what I can do is I can change the summation. Instead of summing over k, I can equivalently sum over r, and then this looks like h of r, x of n minus r, okay? And there you go. Now h is left alone, x is flipped and dragged, okay? And you get the same answer, obviously, right? So it doesn't matter. The order does not matter in convolution. Yes. But it doesn't matter because you're going from negative infinity to positive infinity. So I should be precise. Okay? So, I mean, that's a good question because things like this are done all the time in subsequent proofs. So instead of counting over k, right? You know, 0, negative 1, 1. So instead of counting over these, what you're saying is, let me mark a point here. N, okay? And let me call that point r equal to 0. And this point becomes r equal to 1. This point becomes r equal to 2. This becomes r equal to negative 1. So instead of summing over these, I go backwards and sum over r. Same thing, you'll get the same answer. You satisfied? Good? Okay. Okay, order doesn't matter in convolution. Yes? Yeah. Oh. Thank you. Good? Alright, thanks for catching that. When you see something like that, something silly, please do tell me, because it's probably really silly. Okay, so the next property is very simple to derive. You don't even need a change of variables. Or is the distributive property. So what this says is the convolution of x with the sum of two signals, h1 plus h2, is going to be x star h1 plus x star h2. I'm not even going to prove this. Basically what's happening here is when you have h, which is the sum of h1 plus h2, because you are summing, you can split the summation into two separate sums. And each one corresponds to the individual convolution. Is that clear? Alright. And the fifth one is the last property we'll talk about, is the associative property. I'm not going to write the proof, although it's not a big deal, it's in the notes. Again, it's some change of variables to do the counting differently. Okay, so no big deal. The associative property says that if I'm taking the convolution of h1 and h2 first, and then whatever comes out, I'm taking the convolution of that with x, that's the same as doing the convolution of x and h1 first and taking the convolution with h2. Alright? Again, the proof is in the notes, so it's fairly straightforward. Okay, so these five properties are important. They are also important in the following sense, because how did we come to convolution in the first place in the last lecture? We came to that at the very end, and the context was LTI systems are very special. LTI means linear time invariant. They are very special because once I know how an LTI system responds to an impulse, unit impulse, and get the impulse response, I can predict the response to anything else. In that sense, the impulse response uniquely characterizes an LTI system. If I know if you're LTI, if I know your impulse response, I know everything about you, your social security or bank account, I know everything about it. Okay? So that's of course a property of LTI systems only. The moment I remove linearity or time invariance, I lose all of that. Alright? So, but if if the impulse response is so important, and from that, using convolution, we can predict the output to anything, we should be able to translate some of these properties of the convolution to properties of LTI systems. Okay, and these are very important properties of LTI systems. For example, so implications for LTI systems. So what happens if I take an LTI system with impulse response H1 and take another one with impulse response H2 and connect them in parallel to generate an output. So the same input X is fed to both, and their individual outputs are summed to obtain Y. Okay, so it's a parallel connection of two LTI systems. All right. So what is the first output here at the output of the upper block? X is the input, H1 is the impulse response, so the output is X star H1, right? And then the output of the second block is X star H2, so therefore the output of the parallel connection is the sum of those two, X star H1 plus X star H2. But then the distributive property tells me that this is the same as X star H1 plus H2, correct? So therefore the implication, going back to the LTI system, is that this system, the parallel connection, is equivalent to another LTI system, an equivalent LTI system, whose impulse response is the sum of the two individual impulse responses. Okay? So connecting two LTI systems in parallel amounts to adding the impulse responses, and you can compose them into one single LTI system. All right? So that's one property. Let's also talk about the series connection. So let's say I have X, and then I pass it through an LTI system with impulse response H1, and then whatever comes out of that becomes the input to another LTI system with impulse response H2. So the output at the end of H1 is of course X star H1, right? And X star H1 is now the input to the second block, so the output here is X star H1 star H2. You all agree with this? Okay? But then use the associative property at the very top. That tells me this is the same as X star H1 star H2. Yes? So what's the conclusion? Connecting two LTI systems in series amounts to having a new LTI system, a composite LTI system, so to speak, whose impulse response is H1 star H2. So if you're connecting LTI systems in parallel, add up their impulse responses. If you're connecting them in series, convolve their impulse responses and get an equivalent LTI system. Alright? Now, at this point, I can go one more step and claim that because of the commutative property, H1 star H2 is the same as H2 star H1, right? That was our third property, the commutative property. And just the way we compose series connections into a convolution, we can split a convolution into a series connection, right? So I can say that this is the same as X H2 H1. You agree? Okay? So what that means is, after all these steps, is that if I take two LTI systems, connect them in series, and then I change my mind and I swap the order, nothing changes. You get the same behavior. All right? So you can swap LTI systems in a series interconnection, and nothing changes. Okay, that again is a remarkable property. You don't necessarily have that when you don't have the LTI property. Can you give me an example where two things will not swap? Let's say, forget about time variation. Let's just take memoryless systems. System 1. Okay. System 2. So give me two such systems, memoryless even. You don't need any memory in these systems to give an example, where changing the order doesn't give the same answer. Come on, quickly, you should be able to say something. Yes. So it's everything to 1. What do you mean? Oh, okay. So all right. So y equals 1. Doesn't even care about x, right? Is that what you're saying? Okay. 1. And what does system 2 do? It could even be linear at that point, right? Yeah, y equals x, let's say. So 1 comes out no matter what x comes in, right? Wait, but that doesn't... Wait, doubles, you said doubles, right? Yeah, okay. 2x. So 2 comes out. If I change the order, what happens then? Yeah, again 1 comes out because system 1 appears at the end. It ignores the input, gives you 1 again, right? So that's one example. Will not commute. Okay? Or you can take any two nonlinear things. Two nonlinear things usually don't, you can't change their order, right? So, if one is square, yeah, I mean, I'm not going to waste more time. Is that clear to everyone? Do you see why linearity is essential? So this particular guy is not linear because its graph is flat equal to 1, right? Okay. Non-linear. All right. So it's clear then the linearity component in LTI is critical for this swapping property. But without messing with linearity, just take two linear systems, make them time varying. At least make one of them time varying. Can you give me an example where I lose the swapping property? So let's say, I'm going to restrict this a little more. Let's say system 1 is linear, but time varying. System 2 is even LTV. Removing the LTI, I'm sorry. Removing the TI-ness of one of the two systems is already enough to disrupt the property of swapping. So let's construct an example like that. Any ideas? Okay. So let's make it continuous time just for the expressions a little easier. So I'm going to take the LTI. So what you said is an LTI system. It's a delay, right? So let's say this system is defined by this relation, y of t, and let's call the input v, right? V of t minus capital T. So it basically delays the input signal by capital T units of time and gives you back. Right? So why is this a linear system? Well, I mean, you're getting the same output, only shifted in time, so linearity is definitely there. It's time invariant because I'm shifting by the same amount no matter when you give the signal to me. My rule, the rule that I apply is the same. You give me something, I delay it, give it back to you, right? So I don't change my rule over time, right? So this is an LTI system, just delay. Last lecture, we had an example of a system that was time varying, and that was basically scaling time by a constant different than 1. 1, of course, was a scaling thing, right? So what that means is the relation is v of t is equal to x at. Right? Alright, so why do these two things not commute? So if I apply, let's say I apply an input like a pulse that starts at time -2, ends at time 2. So that's my x of t. Okay? What is the output? Let's say a equals to 2, right, for lack of a better number. So what is the output? So I'm scaling the time by 2. That means I'm compressing by a factor of 2. So the pulse now starts at -1, 1, and that's it, right? And then let's take the delay here for system 2 to be just 1. Alright, so what I get at the output is a pulse that starts at time 0, ends at time 2. Okay, so this is my output. Let's now change the order. Okay, let's see if I can squeeze this in. Now let's take the signal, delay it by 1. Okay, what do I get? It's going to look like a pulse that starts at -1, lasts until lasts until 3. Agree? And then the second system, because we swapped the order, that's going to scale time by 2. And what do I get at the end? So now it starts not at -1, but -1/2, right? And then ends at 3/2. Okay? And obviously what I get here is not the same as the output y of t above, which was the output when they were ordered in one way. Changing the order of the two systems led to a different result, right? Sorry, you were giving me an example. I hijacked your example, but I guess you had probably something along these lines. Okay. Yes. I mean, why did I need an example? This was already a good example, right? You remove linearity and you lose this swapping property. I just wanted to show you that linearity is not the only culprit to destroy that. Time variation can also do that. But only because last time we talked about, the scaling. If you interpret this as a system operation, that is a time varying operation. So that was a simple example to be linear but not time invariant. Okay, questions? All right, so I guess it's time to move on. Actually, I've been watching Piazza now and then. I usually give you time to figure it out on your own. And it's better when somebody else explains to something to it. It's clearer that way, I found. But one of the confusions was, about how these, shift and drag and all these things affect the output, right? So let's take advantage of this example to practice a little bit, and then we'll take a short break. So in this example, we passed x of 3 with the first system that scales time by a, right? So the output, what did I call the output? Was it v, right? So v of t is equal to x a of t, right? And then the second system delayed by capital T. So y of t is v of t minus capital T. let's try to express this in terms of x. In other words, let's just substitute v of t equals xat. What do I get? Maybe you can chime in and tell me what you expect. It should be x of what? A, I understand, but you said A first. Is there okay. Like this? Are you sure? Do you all agree with this? Or is it this? Okay, so I can try to explain this to you, but it's important that you sit down on your own and make sure you understand what happened here, okay? So even whether or not I can explain it clearly, okay? So to determine the output at time little t, okay? I'm looking at the input signal at time t replaced by t minus t, right? So basically what I have to do is replace little t by little t minus capital T. Okay? So, and once I do this, this t here gets replaced by t minus t. That's why the whole thing has to be multiplied by a. Okay? Now, if I change the order, let's do it that way. X of t, delay by t. I get a new output. Let's call it z this time, z of t, and that's equal to x of t minus capital T. Then scale time by a. Okay, what is the output? Let me call it y hat of t because it's not the same as changing the order doesn't preserve the output. So what is the new output? It is z of at, right? So if time is equal to 1, right, evaluate z at time equal to a. Okay? So what that means is I go back here and replace little t by at. So the result is going to be x a t minus capital T. Right, that's what you said initially, but this is the other way around. Okay? Obviously, these two are not the same things, and that's why the previous example worked as a counter example. In one case, you have little at minus little a big T. In the other case, we again have little at, but only a single t. That's why the two things don't necessarily match up. Okay? So make sure to walk through this on your own without anybody telling you what to do, and make sure you understand these final relationships we're looking at. Okay? Okay, I said break, but I won't give you. I will give you a break in 2 minutes, but I'll do one little thing and then give you a break. Okay? All right. So we talked about convolution, properties of convolution, and translated them to be properties of LTI systems because convolution is so intrinsic to LTI systems, right? So if the impulse response is all the information we can get from an LTI system, it's uniquely characterized as an LTI system, then all the other system properties we talked about in the last lecture, like a memoryless system or causal system, stable system, right? All those properties we should be able to judge for an LTI system by just looking at the impulse response, right? Because the impulse response hides nothing from me. It's all the information I need about an LTI system. So I'm going to talk about first, before the break, because that's easy, how to judge or determine causality of LTI systems from the impulse response h of n. Any ideas? H is the response to an impulse, right? So causal means you can't predict the future. You can't do fortune telling. You can only respond to what's happening now or what happened in the past, but not to the future. You don't know the future, right? That's what causal means. Non-causal means somehow you can see the future and react to it. And that's physically can be meaningful if you're just processing data that sits there. In that case, future means data that's sitting there, that's indexed to be the future, but future doesn't mean temporal future. So what would you think? What would be the condition? Can you give me a simple condition? Check this property about H, the impulse response, then you are for sure causal, or vice versa. If H is such and such, this is not causal. Before zero, because before zero, there was no impulse, right? Impulse response means your response when you receive an impulse at time equal to zero, right? Anything before time equal to zero, how did I even know it was coming, right? So basically the condition is simple. Make sure, for causality, that h of n is zero when n is negative. Okay, so causal if and only if. Have you ever seen an if with two f's? It means if and only if. That means it's a necessary condition and a sufficient condition. And this is true. Okay? So that means if h is 0 before time equal to 0, you are causal. And if h happens to be non-zero for some negative n, then you're not causal, period. That's the test. Okay? Why is this true? This is actually very simple to argue. We know that the output is the convolution of x and h. And the definition of convolution is sum from k negative infinity to infinity, x of k, h of n minus k, right? Now, actually, let me, wait. It's better if I use the commutative property, because then the argument will be simpler, and instead flip and drag x and leave h alone, okay? Now, if h of k is 0 when k is negative, that means this sum here is equal to the sum starting at k equal to 0 and going to infinity, right? Because for any negative k, h was 0, right? So the product is 0, right? So then it will be x of n minus k, h of k. So if you look at these terms, you only have 0 or positive values of k, right? That means you care about x of n, the present value of x. You care about perhaps x of n minus 1, the past value. But you'll never have anything like x of n plus something, because that would mean a positive k and positive negative k, and negative k's are eliminated because of this, right? So therefore this depends only on x of n minus 1, x of n minus 2, etc. And these are all past values, right? So therefore no future involved, not future values. Okay? So that tells me that if this property is there, then I'm causal. Just for completeness, let me argue the opposite. If that property is not true, then I'm not causal. Okay? It again follows in similar ways. What does it mean if I don't have this property? Like what's the converse of this statement? H of k equal to 0 for all negative k's, right? That's my statement. What is the opposite statement, the converse of it? There is at least one negative k where that's not true, right? So, so with k bar, let's call that one bad apple, to be the one, right? Let's call it k bar, such that h of k bar is not 0. But then again, if you look at this expression and look at the value at k equal to k bar, okay, now we're looking, look at this expression where k starts at negative infinity, okay? So y of n depends on this expression here with k equal to k bar. So that's going to be x of n minus k bar, h of k bar. This guy is not 0. We can't ignore this term. So that means this input is essential for the output, right? The output is dependent on this input. And k bar being negative, that means it's a future value. If k bar is negative 1, say, this is x of n plus 1, right? So this is a future value of input, okay? Therefore, not, that's my arrow, okay, not causal. Okay, so let me clean up my statements. So this was a proof of the sufficiency. In other words, if I have this property that h is 0 for all k less than 0, then I'm causal. So we concluded that. And the necessity statement was, if not, then not causal. Or the contrapositive of that is, if causal, that property is there, right? So if not, we rewrote it in this form. There exists k bar negative such that this is the case, and we argued that that will lead to non-causality. So we have argued both sides of if and only if, right? Both necessity and sufficiency. Okay, let's take a break now, 5 minutes. So I just wanted to make sure this was clear. So sufficiency here meant that this condition 0k for all k less than 0 implies causal. Okay, this is what went in here. Okay, necessity means causal implies that the causal system must necessarily have this property for all k. Okay, but to show this equivalently, you can prove the contrapositive, which means not. Have you had any logic course or maybe somewhere? What notation do you use for not? Or that, okay. So not h of k equal to 0 for all k negative implies not causal. Okay, so the two statements are the same. Therefore, we found this easier to prove, and basically that's what we did here. Okay, in case you lost the structure of the argument here. So the not of that means there is a k bar that is negative for which h is different than 0. Okay, and then we went through the steps and showed that this implies not causal. Okay, that was the structure of the proof here. All right, so let's look at some examples. I know better not to give you two proofs in a row, so examples always ease the tension a little. So two examples from last time. One is the moving average system, where we defined an output to be the average of previous, current, and next inputs. And then we talked about the accumulator, which is like a counter. So this is defined by a difference equation. yn minus 1 is equal to x of n, and you would initiate this at 0. So before time is equal to 0, your counter says 0, right? And then whatever comes in, it adds it up to the previous value. Right? So it's an integrate. It's the equivalent of an integrator in discrete time, right? So we discussed whether these were causal or not, just looking at the structure of the equations, right? And for the moving average, is it causal? Does it depend on the future? Yes, so it's not. Okay, so this guy makes us not causal, right? Whereas the accumulator is causal because the output at this time depends on the output at the previous time and the current input, nothing about the future. All right, so we already know those, right? I don't need this test about the impulse response to convince you that the moving average is not causal and the accumulator is causal. But just for the sake of an illustration, let's do it using this impulse response test. What is the impulse response of a moving average? What comes out if the input is an impulse? Yeah, but in this particular example, there are 3 data points. So 1 over 3, right? So 1 over 3, otherwise it will all be 0, right? So at time, before time -1, I'm taking the average of all zeros, right? Only when time is equal to -1, I start taking the average of this, this, and this. So at that point it becomes non-zero, it becomes 1 over 3, right? At time 0, I'm taking the average of 0, 1, 0, still 1 over 3. At time 1, I'm taking the average of 1, 0, 0, and afterwards it goes back to 0, right? So this is our impulse response, H of n. All right, what is the impulse response for the accumulator? Accumulator just adds up the inputs, and we define it by a difference equation. So before time equal to 0, it was 0, right? So it was 0. At time equal to 0, Well, what's the input now? The impulse response means the input is an impulse, right? So at time equal to 0, a 1 arrives. So we increment the output to 1, right? At that point. What happens after? What arrives after that? Nothing. The input is an impulse. Impulse comes at 0 and disappears forever, right? So from that point on, you have nothing else to add to your 1, so it stays at 1. Right? So do you recognize this signal? Right, so the impulse response of an accumulator happens to be a unit step. Right? Anyhow, so this is how we find the impulse response for these examples. But the question here is, can we verify that this is not causal and the other one is causal? What makes the one on the left not causal? This one. Here's a value of h for a negative time. Right? How did it know an impulse was coming? Unless it's a system that can see the future. Right? That's what makes it non-causal. And why is the accumulator causal? Because the impulse response is all zeros before time equal to 0, and this is the test for causality. Yes? Some questions again, isn't it? Right, it fully characterizes the system for an LTI system, yes. And the question is? Well, wait, what does that mean? So, I know the response to an impulse, and you're saying it gives me enough information that using that, I can produce the outputs to another input. I can calculate them. Yes. Only if it's LTI. Because the last example in the previous lecture was the moving average system. I'm sorry, the medium filter, for which the impulse response is all zeros, right? If that property was there for that system, you would think that the medium filter always gives us zero output. That's not true, right? That's because it's a nonlinear system and doesn't have this property that the impulse response tells us everything about it. There's a lot of secrets that you don't know about it, right? It told you nothing. It says my impulse response is zero. Like, there's a lot of things underneath. Other questions? Okay, no then. All right, so I'm not going to belabor this, but let me ask you a quick question. So if your goal was to check if a system is memoryless, if an LTI system is memoryless or not, what would you check about the impulse response? The way we defined memoryless was it can depend only on the current input, not the past, not the future. I mean, the memory sort of indicates past only, but in the definition, we also included the future, okay? Memoryless means just react to what's happening now. Don't forget the past, don't see the future, right? So what property of the impulse response will tell you that? All values should be zero except at the origin, because impulse comes at time 0, right? You can react to that at time 0. Okay, so your impulse response at time 0 can be non-zero, but everything else has to be 0 because I have no memory. The next moment I don't remember there was an impulse, right? And before it came, I didn't know it was coming, so it was all 0. Yeah, if you're non-causal, that already means you are dependent on a future value. And because of the way we define memoryless, you can define it in other ways. You could have defined it to say don't depend on the past, in which case it wouldn't overlap with causality. But what you're saying is true according to the way we define it. Okay? All right, any other questions? All right, another more interesting property is stability, right? Stability meant bounded inputs generate bounded outputs, right? That was our definition of stability. So how do we determine that from the impulse response? All right, I'll tell you the answer, and then we'll discuss why that's true. Okay? An LTI system is stable if and only if, the second F, I take my impulse response, h of n, take the absolute value, and sum over all n's, and the result does not blow up. That's again maybe a mathematically iffy statement, but basically if I want to write it in a more accurate way, I would have probably said, well, let's discuss this. I'll apologize to the math guys later. Okay? So that basically means the absolute value of the impulse response is not summable. If it's not summable, is summable, I'm sorry, it does not blow up. So therefore, this condition is necessary and sufficient for stability. All right? And we'll argue both. Okay? So let's first show that this property implies stability. So I'm going to assume that this is indeed true, and I'm going to convince you that the system must be stable. Okay? How can I convince you that a system is stable? What is stability? If the input is bounded, you're sure that the output is also bounded. Okay? So you're going to assume that. Okay? You'll also assume the input is bounded. Assume all input values are less than some bound capital B, B for bound. Okay? So there's a hard number such that x never exceeds that, either in the positive direction or negative direction. Okay? And show that y of n has a similar bound, another b bar, or p02, whatever you want to call it. Okay? So that's how we're going to do that. So we'll assume this property is true again, and then we'll assume the input is bounded, and we'll argue that the output is bounded, so that will take care of the if part, right? If this is true, then the system is stable. All clear? Okay, clear because I don't know anything yet. All right, so how can we show that? What is output in terms of the input x? What's the relation that determines the output of a LTI system? It is the famous operation called convolution. So y of n is sum over all k's, x of n minus k, h of k. I changed the order because we know that doesn't matter, right? So in the definition, h was the one that got flipped and dragged. I did it to x. You'll see why in a second. Okay, so that's the fact for LTI systems. If I take the absolute value of this, right, it's the absolute value of this, right? I haven't said anything. It's a vacuous statement, of course. You know? And then this expression relative to this expression is bigger or smaller? Tell me that. Which one is bigger? The one on the left or the one on the right? The one on the right is bigger because you added a bunch of numbers on the left, then took the absolute value. On the right, you took the absolute values, then added, right? If some of these numbers were negative, that would have brought the expression on the left to be lower than the one on the right. Okay, so this is an upper bound. All I'm trying to get is a hard bound on y, the absolute value of phi, and that will conclude at least one part of the proof, right? So therefore, finding upper bounds is fine. Okay. Now, the absolute value of a product versus the absolute value of individual things multiplied. Which one is bigger, or are they the same? They are the same, right? I mean, they are both positive, same magnitude. So here we haven't lost anything. It's actually equal, right? Now, we're doing a summation here. X, I know, is a bounded input. That means I have a bound on it, a b, that this is always less than. Right? So would you agree with me if I then said this must be less than b times sum over k h of k? You agree with this? Inside the summation, you have your h values. They are getting multiplied by a different number every time, but that number is always less than b, or at most b, right? So if I pretend that it's always b, that's only an upper bound. And then I can take b out of the summation. All right? But because of what we assumed, that this property is there, the sum over all h's, absolute value, is bounded. Okay, there's a hard bound on this too. Okay, therefore, y of n itself is bounded. Okay, so this whole thing has a bound, right? Agree? Therefore, y of n has a bound. We're done. Bounded inputs imply bounded outputs. Yes? Well, because x, this is our, we have two assumptions, right? This is true. First, the property we want is there. Second, the inputs are bounded. So each input value is bigger than b. I'm sorry, smaller than b, right? And that's what we use. Say it again. Y is bounded because, do you agree with all the steps up to the last one? So this sum of h absolute value, it doesn't blow up, right? As I sum the values of h, it does not blow up, right? So therefore that sum, there's a hard constant on it that serves as a bound. That sum will never exceed that. That's the assumption, so that's the condition here. Okay, so I can state this more precisely as this. Okay, you asked for it. Let's say n h of n is less than some number. We already used b, so what's your next favorite letter? D, okay. Doesn't sound like bound, but okay. So there's a number that serves as an upper bound on this, right? No matter how I select capital M. So that's basically what this property means, okay? Again, I always take a shortcut putting negative infinity less than infinity, but really that means that, okay? For all M. So no matter how I make this window negative M to big M, how large I take that window, there is a bound that I will never exceed. Okay? So therefore, instead of, let me make this a little more precise too then. So I can just say this is less than or equal to D, right? So therefore this is less than B times D. So, okay. So this property here is called absolute summability. So this, you say that the impulse response is absolutely summable. And it doesn't mean, it means that the absolute value, after you take the absolute value, it is summable. It doesn't mean that, it's definitely summable, without a doubt summable, okay? So, all right. So that's that. And so now we have to argue the opposite direction. We have to argue that if that property is not there, we are not stable. Okay, that's a little more intricate, but I'll go through that very quickly. Okay, part 2 of the proof is the other direction, where stable implies h of n over n is bounded. Okay, again, we can do the same trick we did in the other case. We can use this contrapositive argument, right? So what is the opposite of that? This is infinity. So this, as I do this operation, as I do this sum from negative m to m, it will keep growing. I will never be able to find a bound that works for all m, right? That's the opposite. That's the contrapositive argument. So I'll quickly write that as h of n over n is infinity. Okay, so that's the opposite of this, right? This is negation of this. That should imply the negation of stable, which means unstable. And unstable means output unbounded, even for a bounded input. Well, that's not very precise, so I should say bounded input can give unbounded output. Okay, so I'm not going to spend too much time there, but this is by basically construction. The proof here in this direction is constructive. So I give you an h that fails this property. So we assume h is like that, right? And we construct a malicious input, which gives us an output that is unbounded, even though the input itself is bounded. Okay? Here's a bad input, a bad guy. Choose your x of n to be the sign of h of negative n. Okay, so I give you an h. I know that the sum doesn't remain bounded, and construct your input to be the sign of h of negative n. Right? Why did I construct it that way? Because if I choose it that way, y of n is basically a convolution, right? Y of n is x of n minus k h of k sum, right? In particular, y of 0 at time equal to 0 is going to be sum over k. If I substitute little n equal to 0, I get x of negative k h of k. But because of the way I constructed my input x, what is that going to be? X of negative k is going to be sine of h of k, right? What happens if I multiply h of k with its sign? Nothing if h is positive, and you flip the sign if h is negative, making it positive. Therefore, you get the absolute value, right? So here you get the sum over k of h of k, and because of this assumption, that is infinity. And here you go. An input x of n that gave us an unbounded output. Is x itself bounded? Yes? No? Because it's the sign, right? Sign is either positive 1 or negative 1 or 0, right? So it has to be bounded. So by construction, you can create an input that's bounded that gives us an unbounded output, therefore showing us instability. Okay, so that's two sides of the proof. It's in the notes. You can quietly go over it on your own and come back and ask me questions if you have any questions. Now let's go back to our famous examples, the moving average system and the accumulator. We know their impulse responses. For the moving average, the impulse response is this. For the accumulator, the impulse response is this, right? So tell me quickly if each one is stable or not. Just looking at the impulse responses, because you know how to do that. Does the sum of h from time negative infinity to infinity after taking absolute value, does it exist? For the moving average, does it exist? Yes, it adds up to 1. It doesn't blow up, right? What about the one on the right? The sum blows up, right, as I increase the window for which I'm doing the summation. So clearly, this will be the one on the left. The moving average will be stable. The accumulator will be unstable. Again, these properties can be judged by just looking at the equation. We didn't even need the impulse response, but it's good to do a quick illustration. All right. Okay, so we talked a lot about discrete time systems. And I held off for the equivalent properties in continuous time systems. Almost everything goes through the same way for continuous time systems, but there are a couple of technicalities you have to deal with. Okay? For one thing, continuous time LTI systems, and again, you'll see that convolution is important. But the convolution sum that we've been playing with will now become, guess what? During the continuous time, summations become what in continuous time? They become integrals. So we'll see what the convolution integral is for continuous time signals. Again, convolution will define the response of an LTI system to any input. We'll have an identical statement. If I know the response of an LTI system in continuous time to an impulse, then I can use that impulse response, take its convolution with the input, and produce the output. Okay, same deal. The only question is, what on earth is an impulse in continuous time? So you've seen that somewhere. Math 54, okay. Did everybody take Math 54 here? You took, some of you took 16 instead, right? Did you do delta there? I forgot. I guess not. We may have done the discrete delta, which is obvious, but the continuous maybe not. Okay? Alright, so what is the unit impulse in continuous time? CT means continuous time when I use the abbreviation. Okay? Well, the notation is the same. At least the good news is the notation doesn't change. Okay? Instead of delta of n, I have delta of t. Okay? But how do I define it? Well, the definition is as follows. Start with something like this. A pulse, you see the impulse is a pulse with zero duration, right? That's the case in discrete time. It came at time zero only and disappears, right? So in continuous time, what I can do is I can take a pulse of width delta, okay, and use this to define a function. So let's call this little delta sub big delta of t, and I'm going to set the amplitude to 1 over delta. Why do I do this? Because if I look at the area underneath, what's the area? The area is 1, and that doesn't depend on delta. Okay? Okay, so I just defined a pulse function here that depends on the width, right? What happens if I take delta to 0? It's getting slimmer, but it's not losing any body mass, so it's getting taller, right? Just imagine squishing something, right? What happens to this in the limit? It becomes this weird creature that has zero width, but infinite amplitude. and somehow still area equal to 1 underneath, right? Whatever that means. Well, whatever that means is the definition of the Dirac delta. So delta of t is interpreted as the limit of these class of this family of functions parameterized by delta as the parameter delta goes to 0. Okay? And it also gets a weird notation of its own, or some symbol, let's say. We use this strange arrow, and that denotes delta of t. Okay? Again, when you see this, the way to interpret this is it as something that has 0 width, infinite amplitude, but somehow area equal to 1 underneath. Alright? That's the definition of delta. Blame it on Dirac, I didn't do it. Okay, so Dirac delta function. Alright, sort of makes sense? Okay. Again, mathematically, you might ask yourself what is going on here. There is actually a theory, mathematically complete and accurate, of so-called distributions. Nothing to do with probability distributions, just called distributions. I might, maybe, if we run out of a lot of things to do in this course, like if we still have time at the end of the semester, I might get into it a little bit to give you an idea. Alright, so, but there is a way to make sense of these functions in a mathematically precise way. Alright, so that's our delta. Now, delta has some interesting properties. Very simple ones. In fact, I'll write something and I'll ask you to tell me. It will be that simple. What happens if I take a signal f of t and multiply it with delta of t? So I'm multiplying this weird arrow with, say, a continuous function f of t. What comes out as a result? Well, delta is 0 always, right? Except at that one point, right? So whatever f was at any time other than time equal to 0, doesn't matter. It's going to get killed by delta. So what do you think will happen? Again, a delta t comes out, but the amplitude is no longer necessarily equal to 1, right? What is the amplitude? It's the value of the function at time 0 times delta of t, right? So if I multiply those guys, I'm going to get another delta, but the amplitude or the area underneath is no longer 1, it's rather f of 0, delta of t, okay? So that's a quick property, and the second one is very simple and similar to the first one. What happens if I look at this product? Now we're talking about the delta, not at time 0, but at time equal to capital T. So we've moved this guy, right? So we're talking about this guy, delta of T minus T that happens at time equal to T, right? So what comes out of the product? F of capital T delta of T, right? So, obviously the F doesn't get much out of this multiplication. It gives away everything. And delta just gets the amplitude of F and gets away with it, right? So delta is intact and F is eliminated mostly. Alright, so the last property is the following. If I take my delta and scale its time argument, delta of AT, what do you think happens? It will again look, it was like a needle, right? If I squish it more, it doesn't matter, it's still a needle, but you have to be careful. Let's look at this. Take this function, that was a well-defined function with some width, non-zero width, right? Let's first scale that and see what happens. Okay, what happens? So what will happen is that the width becomes delta by what? Delta divided by A. Does the amplitude change? No, I'm only scaling time. So that remains at 1 over delta. But wait, something happened. The area underneath is no longer 1. What is it? 1 over A. So it kind of makes sense that delta of AT is not going to be delta of T, although it's still really slim and tall. Turns out it's a little less in value because the area is, if A is bigger than 1, then it's going to have less volume underneath, right? And turns out you get the same thing whether A is positive or negative. That's why we use an absolute value for any A not equal to 0. Okay? So these properties will come in handy now and then. It will appear somewhere in some proof or something. It will show up and they'll be useful. So it's good to state them up front. Okay, so here comes the most important part of this discussion. What does this all mean for LTI systems? In discrete time, we saw the following fact. If I apply a delta to an LTI discrete time system, and if the output that comes out is h, the impulse response, then the output to anything else of the same system can be obtained from the convolution of x and h. And that here means ditto. Okay, all this LTI DP, same system. Okay? Turns out the same thing is true in continuous time. Now you're applying the Dirac delta of t, which is the signal that comes in, LTI continuous time system, and define the resulting output as h of t. Okay? And then if the input is actually something else, x of t, again a property very similar to discrete time holds, where I get the output from x star h of t. But what is star? Okay, that's the key question. How are we going to do the convolution continuous time? Yes. It's going to be an integral, yes. Okay, make a guess then. So, right, yes, good. X star h of n in discrete time was sum over k, x of k, h of n minus k, right? Just by pattern matching or whatever you want to do, can you predict x star h of t? Okay, okay for m, but so let's be careful. So the time here was little n, and we used dummy k, right? Now its time is little t, and we need a dummy for that, right? Yeah, I understand. Okay, but m sounds like it's totally fine. M sounds still like an integer a little bit to me. Maybe I'm crazy. Okay, something that sounds a little like t. Tau, the Greek tau. Greek letters always come to the rescue, right? Okay, so just like x becoming x of k, it will now become x of tau, right? And h becomes t minus tau, and then we were summing over k, and now we're going to integrate over tau. Okay? So that is the definition of continuous time convolution. I've proved nothing. We've done nothing here. We just did a little bit of pattern matching and predicted what it might look like, right? I have yet to do the work. Well, again, just like we did, how did we get to this convolution in discrete time? We used the LTI property of the system, and we concluded that the output will look like that, right? So we have to do something similar. How many of you remember how we did this in discrete time? That happened in the last lecture. Yeah. Right, so we took our x and wrote it like this. X of -1 and everywhere else 0, right? Plus x at time 0 and everywhere else we set it to 0, and then you take the value at 1 and get rid of everything else. So if we continue the summation on both sides, we reconstruct x of n, right? Does that make sense? But this guy looks like an impulse, right? It's x0 times impulse. So since the LTI system gives h in response to an impulse, I should get an h in response to this, right? Except it should be scaled by x0, because x0 is not necessarily 1, right? So x0 times h of n is what comes out of this, right? By time invariance, a delta that arrives at time 1 should give us an h that's shifted by 1, right? So using time invariance, this should give us x1, which is just a scaling factor, that there I'm using linearity, right? H of n minus 1. And this would be x of -1, h of n plus 1, because that's delta n plus 1, what we're looking at here, right? And it will give me h of n plus 1 by the time invariance property, right? So in writing these, I already used, linearity as a scaling factor with x's, right? And the time invariance property of the system. And again, by linearity, sum of separate inputs will give us an output that's the sum of the individual outputs. So we can add these up, and that was basically the definition of x star h of n. All right, something similar needs to happen in continuous time. Only now it's a little more elaborate because it's it's not discrete. I can't split into these neat little things, right? Instead, I can do something similar though. Now x of t, I can't quite write it in this form as sum of impulses, but I can do this. Let's say x is like that, right? What I can do is I can do a little staircase approximation to x. Take the value at x0, continue that until time equal to 0, and let's split into time intervals of little delta, and we'll take that delta to infinity to 0 eventually. Okay, and then the smaller I choose delta, the better an approximation this becomes to x of t, right? So the blue one is x of t, the orange one is a staircase approximation of it that I could write in this form. So let's take one of these. Let's take the kth one, k delta. And write colors. Okay, so this bit, I can write this as x of what? Time is k delta, right? So I read the value of x at time k delta. All right, and then what is this bar? I mean, what is going back to our definition of this this guy, right? This delta sub big delta. How can I write this bar here? It didn't come at time 0, but I should be able to write it in terms of this delta sub delta, right? How would you write it? T k delta, right? Okay, so basically this much of the function I can write in this form. Okay, but we have many of these, so if I sum these over k, sum over k of these things, then I've accounted for all the steps in the staircase approximation, right? T minus k delta. All right. All right, so do you agree that as I take delta to 0, this will work? Okay, there's an error here. Let's see what we can see it. So I'm missing a scaling factor. What's the amplitude of this delta function? 1 over delta, right? So I really wanted something with amplitude 1, so multiplying it with this generates that, right? So I just need to multiply this with delta, right? Yes? Okay. So, using the LTI property, if this gives me an output that I will call H delta of t, then this will give me H delta of t minus k delta using time invariance. Okay? And then, if the input is a scaled version of this, scaled by x of k delta, by linearity, I'm going to get the same scaling factor, x of k delta, times h delta of t minus k delta, right? And there was another delta here, so let's multiply both sides by delta, again by linearity. This is going to be 2, right? That means if the actual input to my system is the sum of these k's, I'll get the sum of these things here, again by linearity, okay? So therefore I can claim that the output of the LTI system is the limit as delta goes to 0, 0, 0, 0, of what I see on the right with the summation. X, k delta, h delta t minus k delta. Now, when was the first time you saw an integral in your life? Yeah, there's this Riemann sum type of thing. So this really is, if you twist your eyes and remember your high school days or whenever it was somebody introduced you to integrals, this expression really is in the limit what we wrote here, okay, by the Riemann sum expression, okay? I'm just going to leave it at that. In the notes, you will see that the 5 properties of convolution we discussed at the beginning for discrete time, they hold the same exact way for the continuous time convolution as well. I didn't get to it, but please do read those, okay?